Hello everyone, my name is Devendra Kapadia, and in this talk, Gosia, Konwerska and myself will give you an introduction to the enhanced probability and statistics features in Mathematica 10. Now, to give some background, in version 8, in Mathematica 8, we introduced a large family of distributions, and then we followed up in version 9 with random processes including time series and other areas, and all this has been very successful. So in version 10 our focus was on two different themes. On the one hand, we'd like to make time series a much more useful area for the average person who wants to analyze the data. On the other hand, we wanted to go a little deeper into random processes, and we have done both those quite nicely, and that's what I'll speak about today. So here is an outline of my talk. So we'll begin with time series analysis, which is the core new feature for Mathematica 10, and then I'll move on to transformations of random processes, which I've been working on and quite enjoy speaking about. And then I'll give an introduction to hidden Markov models, which are used in biology, communications and other areas. But at that point we will be ready to go on into a lot more depth with time series, and that's where Gosia will come in and speak about creating and manipulating chronologically ordered data. So that is the plan for this talk, and now I'll begin with the main feature for version 10, which is time series analysis. Okay, so we have two new wrappers, two new functions in Mathematica 10. We have time series and event series, and time series is used to represent data in which we have continuous time, and then event series works with discrete time data. So as an example, here is a time series which contains the temperatures for Houston, Texas on October 16 this year. So you see, it's just a nice wrapper which has all the information inside it, and then what you can do is you can query this time series object to understand what's inside it. So for example, you can say, could you plot the data, and you get a nice plot showing you the temperature variation for that day. Or you could say, give me a list of all the temperature values, and you get that list back. It's all in centigrade. Or you could say, give me the temperature at a particular time in the day, and then you get back the temperature at that time. So you have this new object called time series, which will do everything for you, but is nicely packaged and available for all kinds of extension and analysis. Okay, so as an example of this, let's take an example from personal fitness analysis. That's a big theme these days. We have lots of devices which will record the number of steps which you take or whatever, and then you have the data. The question is, what do you do with it? Okay, so here's an example in which we have the step data for a certain person for a period of 5 months. It's a time series. Now, of course, this data really is data for Stephen Wolfram, and the question you might ask is, how is he really doing over here? Well, it turns out that from many points of view, a healthy goal to set for yourself is 10,000 steps per day. That's a few miles every day. And the question is, how is he doing? So this is a 10K level, which we are trying to aim for, about 5 miles. Okay, and then if you plot it, you get the surprising result. In fact, he's doing really well. So here's the kind of the magic line over here, and you can see that on a number of days he's actually quite exceeding that limit. Okay, so then you could ask, can we compute, let's say, the mean, the median and the max for this data? And you can do it quite easily. So you see the mean is about 10,500 steps, and in fact the maximum is very, very high. Or you could say, could we plot a histogram for the data, and you can get that back as well. So time series is a wrapper, but this wrapper is recognized throughout the system. You can plot a time series, you can perform statistics on time series, you can do histograms, you can do exactly what you desire with it. Okay, so now I go on to the second theme for today, and that is transformations of random processes. Now, the idea is the following. See, we had this function called transform distribution in version 8, which was really quite successful. And the idea over there was, if you have a distribution and you want to define another distribution which is somehow a transformation of this one, how do you do it? And so now we say, if you have a process like this proc over here, then can you somehow or the other make a transformation and define another process in terms of the existing one? So you give yourself a variable x which follows a certain process. You have a notion of time, t, and then you try and transform the process to get new ones. And it turns out that this simple procedure can be used to gain insight into a very large number of areas: stochastic calculus, finance, insurance, etc. And I was quite surprised to see how nicely things work in this new world of transformed processes. Okay, so as an example of this, you see, in reality we typically think of two kinds of process. One is so-called jump process, where things happen in bursts. You have an event, then things go on for some time, you have another event, etc. And then you've got diffusion, which things go on smoothly. But in the modern world, one really needs to combine the two and speak about jump diffusion models. So, in fact, Robert Merton defined a jump diffusion process, which he believed would be a much more accurate, realistic way of pricing options. So here is a process of the type defined by him. You have a jump process J, which follows what we call compound Poisson process. You have a diffusion process, which is Wiener in this case, and together they define a jump diffusion process. So what you can do is you can simulate the process, you can plot the simulated values, you can compute slice properties like the mean, the skewness, and the kurtosis in this case, or you can go a step further and start with the simulation data like I'm doing over here and actually use the smooth histogram function to find out what the slice distribution at a particular time looks like. So you see over here we bring together lots of things from the last 2 or 3 versions into one to model this rather non-trivial idea of a jump diffusion model. Okay, and finally, from my point of view, we need to wrap up by talking about hidden Markov models. Now, the point is this, that you might have a Markov model in which the states are, let's say, x1, x2, x3, but what you observe are not those states which remain hidden, but you somehow observe some different kind of emissions or observations over here, like y1, y2, y3, and y4. Okay, so this is the picture for a hidden Markov model, namely the actual states of the process are hidden and what you observe are some slightly different variables called the emissions. And you can model this quite nicely using the new function hidden Markov process. So this hidden Markov process can simulate, it can estimate, it can do all kinds of things for hidden Markov models. And an example of the new process here is an unfair casino. So the point is, there is a casino in which the dealer will either use a fair coin or use a biased coin. And bias in this case means that the coin will return a head with roughly 75% probability. And then the dealer will switch the coins 2 out of 10 times. Okay, so of course you don't know when the switch takes place, how the switch takes place. What you observe are actually heads and tails. So here is a hidden Markov process which actually models situation. So you have the initial probabilities of choosing the coins, then you have the switch between fair and unfair, and those are the probabilities for the 2 coins. And just for comparison, let's set up a fair casino. And now let's generate lots of heads from both these kinds of casinos. And you see that clearly the unfair casino is biased towards the heads. Then what you can do is you can actually generate a sequence of observations from the process. And you get back a sequence of head, tail, head, 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 etc. Now the question is, given this sequence of observations, can you go backward and figure out what the underlying hidden states were? And that, of course, is a problem which was solved very nicely, very comprehensively by Andrew Viterbi. So we have a scheme of Viterbi decoding which you can apply over here to actually get back the sequence or the probable sequence in which the selections of fair and unfair were done. So here is a plot where you can see when an unfair coin was selected and when a fair coin was selected. So this is the idea of a hidden Markov model, which actually is very powerful and used in many real-world applications, and we have a very efficient implementation of hidden Markov processes. So with that, I will stop over here and hand you over to Gosia for further information about time series. Thank you.
Okay, so my name is Gosia Konwerska, and I will now talk in more detail about the time series and event series. And we're going to start with event series. That's a new object in Mathematica 10. It has been designed to store the discrete data. It's a single path object, so we can define some data list and then define event series. The properties can be accessed by just asking for properties, and we can see the path of the event series. We can extract a single value at a given time, and then we can ask for maybe a value between the data points, but the feature of the event series that it's not being interpolated, and hence the result is a missing value. We can use a list plot to visualize event series. The next time series, this is a object which is designed for the continuous data. It also specifies only single path. We have same data, create the time series automatically. We see the path starts at 0 as the integer times. The feature here is that if we ask for the data points between the for the value between the given data points, we have the value interpolated. We can visualize the path using the list line plot, and we have an option here in the time series that can specify what to do in the situation when the values in between data points are being searched for. So we can set it to none, and then the behavior is just like in case of the event series, it's missing. We can assign a constant method, a constant value between data points, so here 604, and as before, the default, it's the interpolation method with order 1. The other way to specify time series is to input the values and then input timestamps, which could be dates. So here it's starting at the January 3rd, automatic for the end, and then we go in steps of days. And for such time series, to visualize such a time series with dates, the useful function is the date list plot, which will automatically create, put the dates on the axis. We can also input a path, so the time value pairs into the time series, and visualize that. And also, because of this specification, most of the functions that accept argument value pairs will work with time series inputs. The time series can be obtained from Wolfram Alpha, so we can ask Wolfram Alpha for the historical data on the names. And here automatically create a time series. We have a pair of 2 time series. And then this can be combined in a single temporal data object. So temporal data object exists since Mathematica 9, and this has the advantage that it allows us multiple paths, so it's a more complex system. And when we use the date list plot to plot these 2 time series, or just plot the single temporal data object, we get the same result. Other way to obtain the time series in Mathematica would be to use data packlets. So one of them is the air pressure data. And because it's with the times, with the dates as a times, then we can use the date list plot to visualize that. And we also have a collection of examples in the example data statistics, and specifying the last option here, the last input time series, gives us exactly the time series object. You can use date list plot to visualize those. And one more example here, it's the financial data. So asking for Starbucks values of Starbucks on close for the given date range, and right now by default we see that the financial data will return us a path, so that's the first element of the path. Because it's a date, say time value pair, we can automatically create time series and visualize. The catch is that this data, it's not gonna be regularly sampled. The problem here is because of the days and the business days difference. So the good solution would be to create the new time series where we specify our times here with the given step of a business day, and use the holiday calendar to specify the times where the New York Stock Exchange was closed. And then we said that, the time series defined in such a way are regularly sampled. The other way to do it, what I call the bad quick fix, is to specify the option. So we have a temporal regularity option, and if we set it to true, then we create automatically time series, but it is now understood as regularly sampled. The difference here is that our prices too that were defined with the business day, the minimum time increment for this time series is business day, and for the prices free, the minimum time increment, it's really a standard 1 day. Okay, we have lots of functions in Mathematica for descriptive statistics, and these are working when the input is time series or the event series or temporal data. They will ignore the timestamps. So if we have time series, we can visualize. We can calculate the mean and the variance of this time series. We can run the distribution tests, and we can also visualize certain statistical properties, so the quantile plot, or we can have the histogram or box whisker chart. But that works only for the values. Okay, for the manipulation of time series, there are many new functions that are specifically designed and introduced to work with event series, time series, and temporal data. Most of them will start with a time series and then the function. Here is a list of them, and I will not have examples for all of them, just for the few, but I would like to mention them here, and there's a documentation, of course, for each one of them. So the time series shift, that's shifting along the time axis. Time series window, that means extracting a part of the time series. So here we have a time series from January 1993 to 1st of June 2014, and then I would like to take the part of this time series that goes from the 1st January 1993 to, say, the end of the year 2003, and then the TS2 will be the remaining time series, and then we can visualize two parts of the original time series, maybe to highlight one of them for the different time. Time series insert, as the name suggests, would allow us to insert a value into time series. It also allows us to combine two time series. Rescale will rescale the timestamps. Resample, we have go back to the example of the financial data with a Starbucks stock. We created the prices automatically, and we know already that these are not regularly sampled. However, we can so why we care about the regular sampling, because certain functions like accumulate, which now supports time series, may give us so-called wrong answer when we check the values of the accumulated prices versus the accumulation of just values of the prices. We see that they're not in agreement, and the problem is that we are running here accumulate according to the minimum time increment. So what accumulated did was to think that this data must come in days, but we know that it comes in business days. And one way to rectify that, besides the other two options that I showed before, is to use the time series rescale and resample and resample our prices according to business day. And then these are now regularly sampled, and what is important, that we didn't really change the path. So the path of the prices and the path now of the resampled time series, they are in agreement. Our new minimum time increment is business day, and we can accumulate our resampled time series, and we can now check that we are in agreement of accumulating values versus accumulating the time series, and that's what we get. I'm gonna close this section. It's easier to read. Time series aggregate, that's all the aggregating properties. We also have time series map that would map over the values of a time series. Time series thread, it's gonna allow us to thread over multiple time series. Time series map thread that would map over a time series while allowing us to apply a function to both times and values. And then moving map, moving average as moving functions. So moving average is a special case of moving map. If we have data here, simulation from the ARMA process, we can apply moving average, and that will smooth our time series. Or we can apply moving map with quartiles, and then we create a 3 quartiles plot. Okay, and one more thing here, the missing data in time series. So missing data method is an option. It happens that we might have a data like here records, that some of the records will have the specified timestamp and then missing value. And the missing data method will allow us to specify what to do in such case. So I'm going to create the time series here from the values and then explicitly sample by business day, and we have the values which include missing. One way to treat the missing value is to fix a value. So m is the mean of all the non-missing values, and then specify missing data method as assigning a constant m. Or what we can do, we can also interpolate time series. Here you can select interpolation order 1. And this is the result on our plot. You can see the differences depending on what we have done. And so, thank you very much for your attention.